Log on, tune in, find out. Another good idea from Cambridge.
Technology at the same institution here. Let's see, is this working? That's on? Great. Okay. So I'd really like to thank the conference organizers here. I was really delighted when Barry asked me to pick 57 of my favorite topics and just expound upon them. I guess we don't have that timepiece here to make sure I'm off in an hour. So we've got a weapon, so that's good. So you're very, very safe. I wasn't really quite sure what to say, and so maybe I was scaring Barry by not having slides until the very last minute here. But in the end, I decided not to talk about latest and greatest or whatever. I just tried to look at that title of the conference here around productivity and looking at deterministic models and then looking at stochastic models and thinking, well, what are ways that input uncertainty might be linked across these types of approaches to modeling? And so I'll have a few comments about some issues about what are some differences that I perceive between deterministic modeling and stochastic modeling and why that might have some implication for understanding what inputs, statistical inputs in particular, are for computer experiments. So, given that this is a marriage of this deterministic and stochastic crowd, I'll put a little bit of something old and a little bit of something new into the talk. If you want to get coffee in about 3 minutes, all you need to know is what's on this slide. And if you have already had coffee and want to stay for the rest, I'll explain a little bit more on what these 3 points are. So just warning you in advance what I'm going to say. 3 points. The first point is this issue of how do we fit input parameters. One could go out, for example, if you're looking at a queuing system, collect inter-arrival times or service times and try to fit models with what I would call input-oriented data. Or one could do something like observe output processes, like what number of people in the queue through time. So that would be an output of what we in queuing or a discrete event simulation would call more as an output there. And so I'd like to touch on a very fundamental difference here between deterministic modeling and stochastic modeling, is that you can get very different conclusions about the input parameters depending on whether you're taking a deterministic framework or a stochastic modeling framework. So that'll be the first set of concepts that I'd like to discuss a little bit. Second set of concepts that I'd like to touch on at least a little bit is within a stochastic process framework, how one might go about learning about input uncertainty and looking at the distribution. So what is the distribution of that lambda based on real world observations when we're trying to back that through, trying to understand parameters that we would put into a simulation to describe stochastic uncertainty. And then the final little bit here, which I may or may not have time to get to, that's in the last 87 slides, that'll be around this issue of when we have stochastic output, we put the same input in, we get different outputs each time. Well, if we run replications, we can reduce that uncertainty. Sometimes in stochastic simulation, discrete event simulation, I'll use those somewhat interchangeably, there's often this habit of trying to run a lot of replications to eliminate that uncertainty, but we often forget to think about the parameter uncertainty itself, and so that's touching on the W's and the lambdas from Shane's talk. So if I have enough time, I'll also talk about that. Okay. So here's Shane put up a framework, kind of a mental model type of perspective. Here's my little mental model here. We're interested in examining that question about how do we estimate input parameters, and we can either take this kind of input-oriented view or this kind of more output-oriented view, as I just said. So touching on this first point. A lot of the talks that we've seen in the first several days of the conference have been very much oriented around physical systems, engineering systems, where there's often a reductionist viewpoint that can be at play. Take things apart, understand the parts, put things back together. We have large systems of equations. We can understand how the universe might be expanding or shrinking through time. The types of systems that we're often involved with industrial systems, or in my case, I'm often interested in health applications. I'll touch on some health applications here. There are humans involved, and humans don't behave the same way as atoms or mechanical objects. So we're often more at risk if we try to characterize human behavior with input distributions. So sometimes we often find it easier to look at outputs of processes. So in a bakery or in a queuing system for voting, it might be easier to observe that queue length rather than inter-arrival times. Or in a healthcare application that I'm working on right now, we're interested in modeling how patients behave to interventions to try to improve their behavior to reduce the incidence of diabetes, type 2 diabetes. So there it's easier to measure the prevalence of diabetes than to go into people's homes and watch how people are or are not eating vegetables 5 times a day. So these are the types of things, these are the types of reasons we might be interested in looking at outputs. So my mental framework here, given that, is we have some statistical parameters, we have some decision parameters, this is chains X. We may have some environmental parameters, random uncertainty around the world that's changing, and these might be time variant, as Lee suggested. We throw that into our simulation, and out is going to come a bunch of outputs, maybe univariate, multivariate. We may be looking at long time series. We might be running multiple replications to estimate means through time, for example, in these dynamical systems. From that, we might have several types of purposes for doing that modeling. One of those is to just get intuition about the system. So if one parameter goes up, how does the response go up? So that's one. We might also be very much interested in measuring and getting a good prediction. So that's the calibration issue that's been discussed. And in a lot of the applications where I'm seeing, we're not necessarily interested in the exact measurement and calibration. We might be interested in what's the decision that the model leads us to. And so that's kind of the mental model that I'm coming at this with. What is the decision I'm ultimately going to take? So that's the mental model. Now let's touch about these first couple of, this first issue a little bit more carefully. Output-oriented approach to trying to fit the input parameters versus an input-oriented approach. And what happens if I use an output-oriented approach if I've got a discrete model framework versus I've got a stochastic model framework? The bottom line of the next couple of slides, to forewarn you, is that stochastic simulations are not just deterministic functions with some noise added on. So we can't just take our output and then add on some epsilon of x, where x is the input point. That's the key message here. And I hope to show that there might be some interesting ways where you can get royally wrong results and you might come up with bad decisions if you were not to account for that. The simplest possible model that I can think of is an MM1Q, and then I'll talk a little bit more about a little bit more complicated model about infectious disease transmission. The simple model, think about it, the arrival rate of customers, a certain number of customers arrive to a voting booth, takes them a certain amount of time to vote, and then they leave. Now, as long as the expected time to vote is less than the expected inter-arrival time from one customer to the next, if you were to build a deterministic model that flows into a reservoir of people waiting and then people leaving, that reservoir will eventually empty out very quickly. That's the fluid model approximation for queues, if you're familiar with that type of language. On the other hand, we know from Pollaczek-Kinchin formula that the average number of people waiting, if we were to run this simulation for a long time, stochastic model, the average number of people waiting will not be 0. And in fact, it depends on the fraction of time the server is busy, the average service time, and then the coefficient of variation of the service times. So here's an example where just plugging in means into a formula, plugging into a deterministic equation versus plugging into a stochastic equation gives a very different result. So that's kind of the obvious one. Everybody will probably say, well, that's too much of a toy example. Let's go to a little bit richer example, which shows that it's not as obvious. Okay, so the specific example I'd like to talk about is Haemophilus influenza. This is not the H1N1 type of influenza. It's a different type of using the word influenza. It's something that causes a lot of pain in kids. If you have a small child that has had an ear infection, you probably are familiar with this in some form or another. Basically what happens is these bugs get in, they circulate around kids, they inflame the inner ear, so that's this picture of my ear. And if you don't take care of that, you're going to get a lot of crying. So we were interested in modeling disease transmissions in daycare centers because that was a prime transmission source, as well as in small families. We tried to look at, well, how do we build a computer model of that to try to come up with the effect of potential vaccines or other potential disease control decisions for reducing the incidence of infection. That's not your baby picture, I think, is it? Okay. Okay, so there we are. So how many of you are pretty familiar with infectious disease transmission models or feel somewhat comfortable? Okay. So a good half, actually. And there's about a half are not willing to dare to put their hands up for one reason or another. Basically, the summary here is I've got a simplified version of two kind of formats for that. One is a deterministic differential equation model, just to show a structure, and then the analogous stochastic model. And both of these models have a couple of parameters that are common. One is D, the mean duration of infection in days. C, the mean number of potentially infectious contacts for transmission per day. And then beta, given that there's contact, what's the probability that there's a disease transmission? So this is kind of the simplest possible model where somebody might be susceptible, then infectious, and then become susceptible again. Okay. There's a kind of a key parameter there, the product of those three. If that product is greater than 1, typically you have a large outbreak. If that number is smaller than 1, typically disease transmission will die out. So it's a critical thing in public health to try to get that number under 1 through some mechanism or another. Vaccination, for example, to reduce beta, or reduce, telling people to stay home to reduce C. Well, you can build a deterministic differential equation. This is kind of a standard differential equation that describes how the number of infected people should evolve through time. And you can also look at a stochastic Markov chain, which uses the same parameters, except for now the number of infected might go up. You might have an infectious transmission, or it might go down, depending on if there's a recovery or not. And what I'd like to draw your attention to on this slide is that there are two different models, both which use the same exact parameters. And it turns out that the deterministic differential equation is a large population limit of this stochastic model. So these are extremely tightly linked models. Large population limit of the stochastic Markov chain is the deterministic model. So we might ask the question, what happens if we take this type of idea, generalize it to disease transmission for kids in daycare centers and families, in small mixing groups, play groups, and see what happens if we take the deterministic approach versus a stochastic approach? Well, here's the type of thing you would do when you're going for the stochastic approach. You'd have one subgroup of people, another subgroup of people. There's people in the different groups may get sick, recover, etc. And you can describe this as a Markov chain. And what you're going to do is you're conditioning on the fact that not everybody gets cured. Okay, so you're going to condition on the fact that disease is still running around somewhere in the universe. Okay, so that's what this little separating out of this nobody infected in each subpopulation means. Okay, so we can do that, and we can generalize to get the typical differential equation that would come with that. The way we did it in a particular study was looking at each of these subgroups of kids, these dark circles, and those kids might interact in one of two ways. One would be they just kind of meet each other randomly in the local neighborhood playground. That's the center circle, so that the white circles are mixing sites, if you will. So to come back to the disease transmission model we were seeing yesterday, we don't necessarily have homogeneous mixing of individuals. We might be clustering in various geographical sites like the Midas group is looking at. Or these individuals might come in contact with each other within their own group or within adjacent groups, say if there are two daycare center rooms next to each other in the same daycare center. So kids might be mixing into each other in different ways. So we have local contacts, that's this outer ring, and disseminating contacts, that's that middle ring. Now it turns out if you build the differential equation model of that, you get the same exact prevalence as with, independent of whether the fraction of contacts here is bigger or smaller, or whether there's more contacts in the local mixing sites. You get the same overall prevalence no matter what with the differential equation model. But when we have a Markov chain model, and so that's what's being represented here, no matter what the fraction of contacts that are local, the differential equation, the large population limit, always predicts the same prevalence. But when you have a Markov chain where there are 10 people per mixing group, or 20 people per mixing group, or 50 people per mixing group, you end up having a lower fraction of people getting sick. So what does that mean? What's going on there? Well, what it means is that kind of from a health perspective, what happens is disease is eradicated from this portion temporarily, but might be ongoing up here. And then after a while, the disease might spread back here, but then it'll be eradicated up here. So you have a reasonable probability of being disease-free in some local region. That is not captured by the large population limit model. So mathematically, the reason is 10 is not a good approximation of infinity. Okay? So, but the public health interpretation there would be, suppose we go into the field and we observe 50% of the kids having ear infections, for example. We would pick, say, so if there's 50%, we would pick the value of R0, that product, to be 2. Okay? If we were to use a Markov model and try to match the output of the Markov model to match what we see in the field, we'd have, if we picked R0 as 2, we'd predict only 46% of the kids being sick. So we'd pick a higher level of R0. So we would mistakenly presume that disease transmission is much more active than it really is. And that is problematic. Second thing that's interesting here is depending on where the disease transmission is occurring, that's a big deal too. If more of the disease transmission is happening in small groups, say in families or in child care centers, as opposed to disseminating, like in shopping malls where people randomly mix, the mistake becomes even bigger. And so this is one kind of take home here. You come home with very different parameter estimates depending on whether you're taking a stochastic model point of view or a deterministic point of view. Turns out that the decisions you make for disease control turn out to be very different. So I won't go into the other 47 slides on that particular topic if that's okay. Is that point clear? Does that make sense? So it's not just like taking a deterministic function and adding noise. There's something structural, and I think the reason is there's a nonlinear dynamic with these systems, and we don't always have large populations at play. I think that makes it fundamentally different when we try to fit parameters to outputs if we take the stochastic modeling approach. And here's a little picture of a distribution of what happens when we have more local mixing in terms of number of people infected. So on average, you get 40% infected, but here's the distribution. If we have a lot of local transmission, there's a pretty good chance that nobody's going to be infected in your local neighborhood until a much later point in time when infection comes back in. Okay, so what's the take home here? Output-based model estimation for input parameters is important, and you get very different conclusions with stochastic or deterministic framework. And it does have a big impact on the decisions you would make with the models. Okay? So one take home there. A second topic that I'd like to touch on a little bit here, and this will be the last topic, it looks like. I won't try to ram it all in. Better to do 2 than 3 rush. The other one is, how do I infer those inputs if I've got a stochastic model based on output data? Given that I know, I've just claimed that it's important to think about it carefully. What are different ways we might think about it carefully? And what I'd like to do here is switch to a different epidemic application, that is of cryptosporidiosis. There's these little oocysts that swim around in drinking water. And I did a project with the Environmental Protection Agency in the US to look at policy for trying to reduce the number of those oocysts. There was a disease outbreak in the 90s in the city of Milwaukee, Wisconsin, 1.6 million people. 400,000 people got diarrhea from this thing. 1,000 people got sent to the hospital and 53 people died. It was pretty serious. Of the 53 people that died, most are highly immunocompromised, mostly people with HIV/AIDS. So there was a question that the EPA was trying to address regarding microbial risk. That is, do we try to put in a special ozonization treatment into large-scale water treatment plants? So for a city the size of Milwaukee, that costs about $100 million. So that's not chump change. And the other option, and that would clean the water for everybody, but it wouldn't work 100%. Or you could put special filters in the homes of people who have HIV/AIDS or are going through chemotherapy, for example. And those would cost a couple $100 a person, might be a lot of people. And the idea was that if you put it on the taps of those folks, they're not going to be drinking the water and getting ill. Okay, so that was the idea there. So we looked at building some models around this, and we had to try to fit input data because the data that we had to fit a bit of input data and a bit of output data. We had data on how many oocysts are coming through the drinking water system from the Environmental Protection Agency, and then the CDC, which is a completely other organization, had the data about incidence of disease, and so their databases weren't matched up. So we wanted to incorporate both of those sets of data. So we again developed kind of an epidemic model here that both looked at how infection dynamics were going, where people can interact with each other basically and cause infection, or they might drink water, and W is the water contamination here, not the input parameter from Shane's thing. And we also have some dynamics around the water contamination that we might look at there. And then we looked at deterministic and stochastic versions of this beastie, modeling both the human-to-human transmission as well as that water transmission. So I'm going to have one parameter called R0H for the expected number of infection transmissions between humans, and R0W will be the expected number of secondary transmissions through the water, where people might contaminate water, like going into a swimming pool or swimming in a reservoir where drinking water is stored. Okay, so here's the deterministic version and the stochastic version bouncing around there. I've got this output data from the CDC saying how many people are actually infected. I've got the input data from the EPA around how many oocysts are in the water. What I've got here is I've got billions and billions. I wanted to use billions up here. Billions and billions of these oocysts in the drinking water system. And you can see there's just a small amount of variation in the stochastic model above and below that. And then we've got number of people infected on the other axis, and there's quite a bit more volatility because there are a lot fewer people than microbes in the world. So you're going to get more volatility around the equilibrium value of the deterministic differential equation. So what we did was, rather than trying to try to fit the deterministic function, add some noise, and try to fit the mean and variance of that noise, what we did was we tried to solve for what is, for a given set of input parameters, what would the stochastic Markov chain have as a stationary distribution, and use that as a likelihood function. So that was one approach that we tried to build in the stochasticness into the inference process. So for a given set of input parameters, we try to solve or approximate the stationary distribution of the outputs, given the inputs, and then use that to infer with the data. The other approach was to use some asymptotic normal approximations using some structural properties of the Ornstein-Uhlenbeck process. So the Ornstein-Uhlenbeck process is basically a Gaussian process that drifts, if you're not familiar with that, it drifts back towards the equilibrium value, but can have some excursions out, but then it's drawn back as an attractor. And so you can figure out what's the mean and the variance of that thing based on what is the response function. You need to know the response function and the equilibrium value. You throw that in there, and you can get an approximation that's a normal distribution approximation, but it's based on the structural properties of the stochastic model and the limiting attractor there. And so we did both of those, and we found that we were able to take some data. Here's the billions and billions. So 8 million people. Tried to figure out what's the steady state distribution of people infected in New York City, 8 million. Roughly approximated the billions and billions by some fraction between 0 and 1, as opposed to counting all billions of microbes in this water treatment shed. So here's New York City. Here's a couple of very large reservoirs for the New York City water supply system. And we kept track of the counts using sigma to make sure the simulation would run fast, and did some inference there. So we were able to do some inference on that, and it turns out that we were able to actually with this type of process, the maximum likelihood estimate of the maximum a posteriori map, instead of pronouncing that thing, turned out to be pretty reasonable, and we were able to find out that it made sense. It validated our belief that the water loop would be relatively unimportant, and that the human-to-human loop was relatively important. And so that was really good stuff to be able to do that and feed that back to the EPA. Turns out that the degree of human-to-human transmission actually matters quite a bit. Jump up here. So here's the degree of human-to-human transmission on this axis. And here's the ratio of the susceptibility of somebody with HIV/AIDS to cryptosporidiosis if they are exposed to the drinking water that's contaminated versus an immunocompetent person who's not immunosuppressed. And depending on that ratio, it might be better to use the ozonization to centrally control water disease control, as opposed to putting filters in the homes of people who are immunocompromised. And the reason for that is because by reducing the prevalence in general of ozone, you're reducing the likelihood that somebody who's immunocompromised gets the crypto from shaking hands to somebody who drank the water. Okay, so that's what a little bit was going on. The original models that the EPA was using was basically assuming there's no transmission from human to human, so they were going to legislate filters better systematically, and this let them think a little bit differently by using this type of a model. So I think those are kind of the main things that I wanted to touch on there. I won't talk about another. We looked at some mad cow stuff with Jeremy here, and we could say a little bit more about inference with these stochastic processes and how we might incorporate specifically the randomness in a stochastic simulation to try to approximate likelihood functions, as opposed to just assuming it's randomness plus a mean from a deterministic model. So those are the big messages I had here today. I will not talk about this next issue of how do you then use that to actually do something about reducing the uncertainty about Shane's lambda at the voting booth, or uncertainty about the disease transmission parameter models. Maybe we'll keep that for the panel discussion a little bit later today. So, any questions on that?
Do we have questions for Steve?
Oh, very good talk. No questions. Good job.
Oh,
Sorry, I missed you.
one question. Yeah.
So in that last application, the drinking water, the data, depending on how you try to boil it down, and this happens in lots of problems, and, it could be this whole time series of counts, right? Or you could grab features of that.
Yeah.
And I was just curious, what sort of process did you go through to decide what you were going to use as something you were trying to match for your likelihood?
Well, we had a couple of different sources of data, and we don't have real-time data, so the CDC, for example, will publish weekly incidents. They don't publish incidents as a time series. We don't know exactly the minute everybody was diagnosed. In a lot of cases, they're not even diagnosed. So we knew the data was dirty, and so we kind of threw that in. But the data is spaced out enough, and we tried to take advantage of that. As part of what we did here is we assumed that the stationary distribution at time point 1 was uncorrelated with the distribution at time point 2, which was a week later. And because we took advantage of some structural properties in the system, like fast modes, water contamination would converge very quickly to its equilibrium value given the number of people infected. So we used that to kind of build in a little bit of extra independence assumptions, and we use that in the likelihood model structure.
Okay. Next speaker again.